Hello and welcome to Physics 297, the independent study in modern physics that we're doing in the spring of 2001. Um, my name is Dr. Scott Ginelli. I'm going to be overseeing the class, but I thought I would give a little bit of an introduction and basically go over the details of the syllabus and then give a quick backdrop, setting it up for the beginning of our discussion of special relativity, which we will start on Wednesday. So let's start by looking at the syllabus. So we're going to be covering theory of relativity, black body radiation, Planck's constant, the photoelectric effect, Bohr's atom, the wave function, Schrodinger's equation, the uncertainty principle, atomic spectra, uh, a little bit about solid state physics, about molecular spectroscopy, nuclear physics, and particle physics, and then ending on cosmology. So we're going to be covering the full gamut. We're not going to go into a whole lot of detail because you can't cover everything that we're talking about in this class in a lot of detail in one semester. There will also be a lab portion of this class, which will partially consist of experiments that hopefully we'll be able to do in person given the size of the class. And also, um, there'll be some computer projects to go, to fill out the lab portion of the class. So uh, you'll be solving problems just like you've done in physics 1, 2, and 3. You're going to you'll be able to understand how modern physics developed, um, do some basic applications of the Schrodinger wave equation, um, and basically apply critical thinking uh, to the class. The lectures will be online and asynchronous. I will record them, and from there you'll be on your own as far as watching the lecture, reading the textbook, digesting the information. The problem solving sessions, the first of which will be next Wednesday, February 3rd, and the lab classes, which will start this Friday, those will be online and synchronous unless it's a lab class that we're meeting in person. So if they're online and synchronous, you're going to be meeting at a specific time. And so I believe for Wednesday, let me pull that up. For Wednesday, we will meet from 12:30 to 2:10. And then on Friday, the lab class, which will either be in person or it'll be online synchronous, that will be 12 o'clock to 1:50. And so our first synchronous meeting will be this Friday. And then starting next Wednesday and every Wednesday through the rest of the semester, we'll be meeting synchronously at 12:30, but not this Wednesday. This Wednesday is going to be an asynchronous lecture. So getting back to the syllabus, my name is Dr. Scott Ginelli. The email address is gianels@sunysuffolk.edu. The office hours are Monday and Wednesday from 11 to 12, Tuesday and Thursday from 1 to 2. We are going to be using the Giancoli book, the book that you've used for physics 1, 2, and 3. The grade distribution, there will be 3 lecture exams, and so there'll be no drops. So they're going to be 15% each. The homework will be 10%. The lab reports and computer exercises that you'll be doing on Fridays will be worth 12.5% of your total grade, or 1/8. The 2 lab exams, the lab exams, whether it's the midterm or the final, will include questions based on the computer exercises as well. But there'll be 2 exams, and they will combine for 12.5% or 1/8 of your total grade. So what you do on Fridays will amount to 1/4 of your total grade. And there'll be an oral presentation, um, which I'll talk about a bit further as the semester goes on, but that will be 20% of your grade. And so I'll talk about what I want to do for that as I go on. That's going to be something that will develop, like I said, as we move on. There'll be 10 lectures, one for each chapter of the textbook, except for special relativity, the first chapter, which will cover 2 lectures. They'll be posted at a specific date. So the first lecture on special relativity will be this Wednesday. The second one will be posted on Monday. And you'll review them asynchronously, meaning on your own time. The problem-solving sessions, there will be 9 of them. They will meet on Wednesdays. There'll be 1 per chapter. There'll be 6 assigned problems, which we will work on together. You'll be doing most of the work, but if you need help, I'll be in the room with you. And then you'll have 4 problems that'll be assigned for homework. And the homework will be due the next class section. So the problem-solving sessions will typically be on a Wednesday, and the homework will be posted on Blackboard on Monday. I will give an extra day because of President's Day on the 15th. I will give an extra day to do that homework, but I will post the lecture on February 15th, which is President's Day, and so we'll keep a steady Monday, Wednesday, Friday schedule throughout the semester, and there won't be interruptions. So I'll post the lecture on President's Day. You don't actually have to look at it that particular day. You'll have the Tuesday as well. But again, just read it on your own time. The homeworks will be graded out of 50. There'll be 10 points for each homework problem, plus 10 free points for class participation. That's not going to be that big of a concern because you're going to be working on the problems together in class during the problem-solving session. So I'll be able to see that the both of you are participating. The laboratory experiments, ideally, I'm not 100% certain, but since it's just 2 of you, I'm fairly confident that we can get clearance to do those in person. I would double check, since I need to do it for myself, on the procedure for going into the for coming into the building. I'll figure out which room and let you know. Otherwise, if we can't do it, there will be an alternative, but I'll let you know as we get closer. And again, the lab class, whether we're meeting synchronously online or asynchronously, is going to be on Friday at, let me just double check that time so we get the right time, 12 to 1:50. The several of the lab classes will involve writing a computer program, so I'll be there for those 2 hours to help you out. If it takes more than the 2 hours, that's fine. Think of it as being like a lab report. You don't have everything. You wouldn't be expected to have the lab report 100% done along with the experiment within 2 hours. So if the computer program takes more time than that, if you need more time than that to finish the computer program, that's fine. I will be present in the Zoom room to answer questions during that hour and 50 minutes. Otherwise, you can always reach me by email or in the office hours. The exams will consist of 4 questions. Again, I will be present in the Zoom room and expect you to be as well. The exams will be delivered to you via Blackboard, and they will be submitted via Blackboard. So you'll be solving problems. There'll be 4 of them. What I want you to do is basically photograph your solutions, take pictures, attach them as one file, and then submit them via Blackboard. And there will only be, are we doing 4 exams? Let me double check. Okay, there are 4 exams. So the lowest of the first 3 will be dropped. So 3 of them will count. The 4th will count regardless. But the lowest of the first 3 grades will be dropped. So let's look at the schedule. So again, class 1, you can assume it's Monday. It's going to meet asynchronous, including today, obviously. And as a general rule, I'll try to have those lectures posted on Monday morning, if not sooner. I apologize for today. Class 2 will be Wednesday, and with the exception of this Wednesday, every other meeting will be synchronous. And then the lab class, whether it's in person or it's a synchronous, a computer assignment, that'll be at a specific time. The computer assignments will be synchronous and online. You don't have to go anywhere. You don't have to leave your house for that. But the experiments will be done in person. So this week, the introduction is what we're doing right now. On Wednesday, you'll have an asynchronous lecture posted on special relativity, or on the first part of special relativity. There will be a computer assignment this Friday on special relativity. So we'll meet synchronously Friday at 12. And basically, there'll be a problem probably from the book. It could be some sort of numerical analysis or something along those lines. But that will be the assignment for Friday. Next week, and this should be part 2, excuse me. Next week, this will be part 2. Next Wednesday, we'll meet synchronously. We'll go over problems from chapter 36. And we will begin on Friday again, hopefully in person, an experiment on measuring the speed of light. Then for week 3, we will go over chapter 37. So the next chapter. Wednesday will be synchronous for problems. And then Friday, we will meet in person to continue measuring the speed of light. The following week, I will still post the lecture on Monday morning. Well, actually, it's not a lecture. It's going to be a review for exam 1. I'll post that on Monday morning, so you can look over that at your convenience on either Monday or Tuesday. So basically summarizing what we've covered in chapters 36 and 37. If you have any additional questions, you can reach me by email. I'll have the office hour on Tuesday. And I think I'll have the office hour before the class on Wednesday. So let me just double check. Yeah, Wednesday, the office hour will be before the exam. So if you have any questions, you can reach me that way. And so the first exam is going to be chapters 36 through 37. It's going to be Wednesday, the 17th of February. So 3 weeks from this coming Wednesday. That Friday, there will be a lab on Planck's constant. And then the following week, we'll resume the lectures. So we have lecture 38, quantum mechanics. We'll do problems on Wednesday. And there'll be a computer assignment on the infinite square well. For chapter 39, we'll do the quantum mechanics of atoms. So again, asynchronous lecture posted Monday morning, or no later than Monday morning. We'll go over problems synchronously on Wednesday, and then there'll be an in-person lab experiment that week, and that'll be on the Rydberg constant. Then the following week, chapter 40, molecules and solids. We'll do problems on that Wednesday. And then that Friday will be the lab midterm. Again, that the midterm we can do online. And so you'll get some questions. And again, you'll submit the answers like a regular exam. March 15th will be a review for exam 2. That exam will be Wednesday, chapters 38 to 40. Again, we'll be meeting synchronously online for the exams. So I expect to see you and online virtually. But the exam will cover the regular time period. There'll be a computer assignment on the Earth's energy balance. Then we move on to chapter 41, and then problems from that, and then a computer assignment on Fermi-Dirac probability. Chapter 42, nuclear energy and the effects and uses of radiation. Problems on the Wednesday, then in person, and that will be the last of our in-person meetings, an experiment on diodes and transistors. Then we get into April, exam 3, I'll post a review that Monday. That Wednesday we'll have the exam. It'll cover chapters 41 and 42. There'll be a computer assignment on semiconductors that Friday. The following week, chapter 43, problems, a computer assignment on binding energy. Chapter 43 is elementary particles. Chapter 44, astrophysics and cosmology. There'll be problems. There'll be a computer assignment on muon lifetime. Then the last week in April, we'll have our 4th exam. And then exam 4, chapters 43 and 44. And the lab final, the final week, there won't be a lab class. So we'll be done the lab. The final week will be oral presentations. And that will be a synchronous meeting. We'll pick one of those 2 days. I guess the Wednesday would probably be the better of those 2 days to pick. You'll give your presentations. They'll be I guess about 20 minutes each. I'll give you some information about the topics. I need to work that out a bit, but we can talk more about that. And then Monday, I'll give you the opportunity to ask me questions as you're working on them. But the actual presentations themselves will be on that Wednesday. But I'll talk about that in more detail as the semester goes on. I'm still sort of formulating what I want to do with that. But that's the basic schedule. And like I said, I'm still working on the topics, but I'll get back to you on that sometime within the next couple of weeks. And so there'll be an oral presentation of 20 minutes and a 5-page written report. And again, I'll have more details over the next couple of weeks as far as what I want you to do. But we're going to be doing that the last week, when the rest of the semester is basically over at that point. Then otherwise, the cell phone policy, not as big an issue. I mean, obviously, some of you, there's a chance you'll be using your cell phones to link in via Zoom, and that's okay. The main thing, cell phones are not a substitute for calculators. Again, that's less important online as it would be in person. If you have any issues with missing a class for religious observance or for military reasons, if you're in the National Guard, for example, if you have a family situation, whether it's a funeral or a medical emergency or something like that, those are excusable absences. They will not be held against you. Um, I mean, I just want to know in advance if if there's going to be some sort of excusable conflict. Um, as far as if you're entitled to extra time in an exam, please let me know. Send me either a picture or a PDF of the paperwork, and I'll know that you have extra exam come or extra time come exam time. Um, Otherwise, if you have other issues, let me know. Academic integrity. I mean, I think that should be obvious by now because of the online nature of the course. You're on your honor to a greater degree than you would be under normal circumstances. But there are still ways to spot if you're cheating. Um, there are ways to figure out if you've Googled the solution to an exam problem, for example. Uh, and plus, if you're relying on cheating, that means you're not learning the material. You'll get exposed when you go to when you transfer out and you go to a new place. If you don't know the material, you'll be behind and you won't be able to make that up. So make an honest effort and get an honest grade, and it will serve you better in the long run. Otherwise, if you have um, if you feel that there's a discrimination, you've been discriminated against or harassed for a reason, whether it's race, creed, color, gender identity, sexual orientation, anything like that, um, you have an outlet at the school. So it's important to make sure that you're aware of that information. There are places you can go, people you can contact and people you can talk to about that. But the campus and the college has a zero tolerance policy for discrimination and harassment of any sort. And it's important, again, that that you're aware of that you have options, that you have resources, and that you have a place where you can contact people. Okay, so with that, I will talk about just give a brief, excuse me, backdrop of leading into special relativity, which we will talk about on Wednesday. So by 1900, pretty much everything you've learned in the first three physics classes was well established. Certainly, Newtonian physics was well entrenched. And there are some basics of Newtonian physics that would ultimately get changed within a couple of years from 1900. You talk about inertial reference frames where the observer is not accelerating, and that the basic laws of physics are the same in all these reference frames. And space and time are considered absolute, and that's the one that gets changed. And so again, we'll talk about that in detail starting on Wednesday. There was another interesting thing that's come up in some of what I've my own research that I've done, and there was a debate about the sun's missing energy, how the sun produces its energy, and how that ties into the age of the Earth. Basically, physicists had concluded, based on the energy that was available, or that was that they understood, that the Earth couldn't be more than a few thousand years old. But there was conflicts coming into play as far as that goes. So you had physicists basically on the side of establishment religion, that the Earth wasn't more than a few millennia old, and part of their evidence for that was that based on what they knew about how the sun produced, and how the energy of the sun, there was no mechanism by which the sun couldn't have exhausted its energy in it could have produced energy for a few thousand years and not exhausted its supply. And so basically, as an explanation of what's going on, I'm referring to a book from the 1870s. And James Kroll was a climatologist, and he was one of the first people to suggest that the ice ages depended on the orbital parameters, how the Earth's orbit changed. So in the 1800s, people were aware that the Earth's orbit varied. Um, the timing of those variations, Kroll didn't get right, and his work kind of fell out of favor because of that. But Milan Milankovitch in the 1930s and 1940s revived the theory, did the calculations correctly, and used the correct assumptions, and came up with a much, much stronger theory. But Kroll had come up with some of those ideas first. But it's interesting when he talks about the energy of the sun. So he's saying, even supposing we limit the geological history of the globe to 100 million years, and I'll explain where he gets that number from. It is nevertheless evident that gravitation will now account for the sun's heat during so long a period. There must be some other source of much more importance than gravitation. So what other source of energy can there be? And then he says it's singular that the opinion should have become so common even among physicists that there is no other conceivable source than gravitation from which a greater amount of heat could have been derived. So where does that 100 million years come from? So he's saying the facts of geology seem to geologists to require a period of much longer duration than 100 million years, and it is this which has so long prevented them from accepting the conclusions of physical science in regard to the age of the globe. So physicists had accepted that, well, the sun, due to gravitational collapse and contraction, was generating the energy, and that it couldn't have done so for that long a period of time. But geologists are saying, hey, wait a minute, the Earth has to be a lot longer than the evidence that we're finding suggests that the Earth has to be a lot longer, or a lot older than the few thousand years of the Bible, or that physics is suggesting. And physicists are suggesting, the physicist response is, well, that would require an energy source that we're not aware of, and which was absolutely correct. But in the late 1800s, the physicists didn't believe that energy source existed. So it's an interesting, and it was the subject of a considerable amount of debate, because not only were the geologists saying the Earth had to be a lot older than a few thousand years, but post-Darwin, the biologists were saying the same things. But it was actually physicists that were being stubborn about this, because they weren't aware of a mechanism for it. That the sun did, as it turned out, have an an energy source other than gravitation that was producing this energy. But physicists were not aware of that in the late 1800s. One of the physicists, and ironically, the one who was most defensive of a relatively young age for the sun and the Earth, was James Clerk Maxwell. And if you've taken Physics 3, you're well aware of his contributions to electromagnetism. And his big contribution started from basically an assumption and a leap of faith, if you will, and following where the mathematics led him. So what was puzzling Maxwell was the fact that a magnetic field was present inside a capacitor, even though there was no a fully charged capacitor, even though there was no longer any current flowing between the plates. So there was still a magnetic field between the plates, however. And, or, even though there was no current flowing between the plates, but there was a magnetic field present in the charging capacitor. And so, how do you explain that? Well, just as Faraday had figured out that a changing magnetic flux creates an electric field, Maxwell assumed that it was possible to go in the opposite direction, that a changing electric flux produces a magnetic field. And if you take that assumption, that explains why, as the charge is building up on the plates of the capacitor and the electric field inside the capacitor is increasing, well, that explains why you get a magnetic field within the sheets of the capacitor. So he sort of put in a correction to Ampere's law that made it consistent with observations inside the charging capacitor. And then he followed where the math led him. So that's where you get Maxwell's equations. And then when you solve for Maxwell's equations in empty space, you get a solution that says, or a differential equation for the electric field and for the magnetic field that suggests that they're both traveling transverse waves, perpendicular to both each other and to the direction of travel, and that the velocity of those waves was too close to the speed of light when he did the calculations for any other conclusion to be drawn other than light is an example of an electromagnetic wave. So he made a basic assumption that corrected an inconsistency. He followed where the mathematics led him, and he wound up coming up with a very profound conclusion. However, even though it explained a lot, it didn't completely mesh with Newtonian mechanics. So people, as Newtonian physics was so well entrenched, most people assumed that there had to be some sort of, that it was Maxwell's equations that needed some sort of correction. So what were the inconsistencies? Well, it's possible to induce an electric field in one reference frame, and then in a different, in a moving reference frame, or in a frame that's moving relative to the electric field, you would observe that as a magnetic field. So how does that work? And if you take Newtonian physics for granted, it doesn't work. And Maxwell's equations don't allow for a different value of the speed of light in different reference frames. So if one reference frame is moving and another reference frame is stationary, or they're moving at different speeds relative to something else, they should measure different values for the speed of light, but Maxwell's equations don't allow for that. So what's going on? So in what reference frame is the speed of light measured? And most physicists believe that there was some sort of absolute reference frame called the luminiferous ether that was an absolute reference frame from which from which c is the accepted value, the speed of light is the accepted value. And then if you're moving relative to the ether, you'll get a slightly different value for c. And so basically, either there existed one universal reference frame, and again, it was called the luminiferous ether, or Maxwell's equations in Newtonian physics were inconsistent with each other. And so basically, option A, either we could find the luminiferous ether and figure out that absolute reference frame, or B, Maxwell was wrong about something, that Maxwell's equations needed some sort of correction to make them consistent with Newtonian physics. However, a third, there was this one person working as a desk clerk in Zurich, Switzerland, who went for option C, that it wasn't Maxwell's equations that needed a correction to be consistent with Newtonian physics, but rather Newtonian physics needed a correction to be consistent with Maxwell's equation. So this person obviously was Albert Einstein. And Maxwell was his idol as far as mathematics and physics were concerned. So he sort of modeled his approach on what Maxwell did. Remember, Maxwell made an assumption that he didn't have proof for, but it fit the observations. He then followed where the mathematics led him, starting at that assumption and then going wherever the mathematics led him. And then he wound up drawing some very profound conclusions. So, that's what Maxwell did. And that's ultimately what Einstein did. That he basically ignored the luminiferous ether. And he said that what if the speed of light is constant in every reference frame? What would be the end result? And so on Wednesday, we will talk about and do some of the math and see where the mathematics led Albert Einstein. And so that will be the topic of discussion for the lecture on Wednesday, and then the lecture next Monday, both of which will be asynchronous. And you'll see that there were some very profound conclusions that came out of that. So with that, I will finish for today. Again, I apologize for the lateness of this lecture, but that is our introductory lecture. And like I said, on Wednesday, we will resume, or we will continue by starting with special relativity.